Okay, again welcome you all of you in the LBCom. We will continue our lecture of last paper solution of December 2010. As we have discussed last question, there is for definition of EMF, reluctance, relativity and MMF. Now next question number B is question 2B. State and explain Faraday's law of electromagnetic induction. Compare statically induced EMF and dynamically induced EMF. Last one is important. Explain Fleming's right-hand rule. So there is a 3 question is composite into the 1 question. So clearly we have to go with each and every before we get 7 mark. So first we explain the Faraday's law of electromagnetic induction. Faraday gives 2 laws for the electromagnetic induction. So Faraday's first law, it states that whenever a flux linked with circuit or a coil, it changes, EMF is induced in it. With a coil, there is a flux is linked, and if this linked flux will be changes, then EMF is induced into the coil. Now we can also say in the different manner, whenever conductor cuts the magnetic field, EMF is induced in the conductor. When conductor cuts the magnetic field, the EMF is also induced into the conductor. Now second law gives the equation. The magnitude of the EMF induced is equal to the rate of change of flux. See the figure. In figure we clearly know the both law. Whenever current will be passes through the coil, magnetic flux is produced. When flux is changed, some EMF is generated or produced, that we called EMF is induced. Now what is the value of induced EMF? The induced EMF is always equal to the rate of change of flux linkage. So when we keep magnet near and far, magnetic flux link with the coil is changed, and on the rate of this change flux linkage, the EMF is induced. So we derive the equation for induced EMF. So first consider that we keep this coil with magnet near and then far. So first we put magnet far from the coil and then we put near to the coil. So let's see the derivation. Flux link with coil at time T1 is N phi1 Weber. Phi1 is a flux at the T1 position and N is the number of turns of a coil. That is when we put the coil far from the magnet. And second time, flux link with the coil at a time T2 is known as N phi2 Weber. So now change in the flux, when we go to the 2 different position, there is a flux will be changed. So flux linkage equal to N phi2 minus phi1. So N phi2 minus N is taken out common, N phi2 minus phi1. So as we know that as per the Faraday's law, the change in flux linkage is phi2 minus phi1, and we can simply put phi for this difference. So change in flux linkage is N into phi. So now rate of change of flux linkage is N phi by T. When we put the rate of change, it is with respect to time, and we give the time by division. So N phi by T. So now derivative on the right hand side, we will get the rate of change of flux linkage is equal to N d phi by dt. We go for the small time duration, then we get the d phi by dt. And as we know that the rate of change of flux is known as the induced EMF. So induced EMF E equal to N d phi by dt. But generated or induced EMF is always opposite to flow the current. So using Lenz's law, we put the negative sign. So E equal to minus N d phi by dt. So this way Faraday's two law of electromagnetic induction gives very best full result is induced EMF is equal to rate of change of flux into number of turns of coil, and negative sign is representing Lenz's law. Let's see the Faraday's law video.
This is most important and basic law of electrical technology. We can say electrical technology is mainly based on this law. Operation of most basic components of electrical system like electrical motors, generators, electrical transformers and inductors, etc. are based on Faraday's law of electromagnetic induction. This law shows the relationship between electric circuit and magnetic field. He found that when an electrical conductor is brought under the influence of a magnetic field, and if the flux linked with the conductor due to this magnetic field is changed, an EMF is induced in the conductor. In this experiment, Faraday takes a magnet and a coil and connects a galvanometer across the coil. At starting, the magnet is at rest, so there is no deflection in the galvanometer. That is, needle of galvanometer is at center or zero position. When the magnet is moved towards the coil, the needle of galvanometer deflects in one direction. When the magnet is held stationary at that position, the needle of galvanometer returns back to zero position. Now, when the magnet is moved away from the coil, there is some deflection in the needle, but in opposite direction. Again, when the magnet becomes stationary at that point with respect to the coil, the needle of galvanometer returns back to zero position. Similarly, if the magnet is held stationary and the coil is moved away and towards the magnet, the galvanometer shows deflection in similar manner. He also found that if these movements are made faster, the deflection of needle of the galvanometer is also more. That indicates faster the change in the magnetic field, the greater will be the induced EMF or voltage in the coil. From this experiment, Faraday concluded that whenever there is relative motion between conductor and a magnetic field, the flux linkage with a coil changes, and this change in flux induces a voltage across a coil. Michael Faraday formulated two laws on the basis of above experiments. These laws are called Faraday's laws of electromagnetic induction. Any change in the magnetic field of a coil of wire will cause an EMF to be induced in the coil. This is known as Faraday's first law of electromagnetic induction. And second law states that the magnitude of EMF induced in the coil is equal to the rate of change of flux linkages with the coil. Now let's establish an equation for Faraday's laws of electromagnetic induction. Consider a magnet approaching towards a coil. Here we consider two instants at time t1 and time t2. Flux linkage with the coil at time t1 is N into phi1 Weber, and flux linkage with the coil at time t2 is N into phi2 Weber. Hence, change in flux linkage is given by N into phi2 minus phi1. Let this change in flux linkage be phi equals phi2 minus phi1. So, the change in flux linkage would be N into phi. Now the rate of change of flux linkage would be N into phi divided by time t. Taking derivative, we will get the rate of change of flux linkage N d phi dt. But according to Faraday's law of electromagnetic induction, the rate of change of flux linkage is equal to induced EMF. So it can be written as E equals minus N d phi dt. The significance of this minus sign is due to Lenz's law. Since the induced EMF opposes the very cause of it, that is rate of change of flux with respect to time. It means change of flux with respect to time induces EMF in the coil. So induced EMF will oppose change of flux with respect to time. Hope you understand. Thank you.
Compare the statically and dynamically induced EMF. First point, what is statically and dynamically induced EMF? EMF induced in the coil is due to the change in a flux of neighboring coil or due to the change of its own flux is known as statically induced EMF. And if EMF induced in the coil is due to the physical movement of either the coil or the field. If coil is movable as seen in the video, or if field is movable, then we can say that it is a dynamically induced EMF. But if there is any physical movement and EMF is induced into the coil due to the change of its own flux or due to the change in the neighboring coil flux, it is known as a statically induced EMF. Statically induced EMF is given by epsilon or E equal to minus L di by dt. Why it is L di by dt? L is a self inductance, di by dt is rate of change of current. Due to the change in the neighboring coil or in a self coil, the EMF is induced. So it is given by induced EMF E is equal to minus L di by dt. EMF induced in dynamically is E equal to BLV sin theta. Sin theta is representing the angle between field and conductor. Here the principle of mutual inductance is used in the working of transformer and induction motor. Transformer and induction motors are work on the principle of mutual inductance, and it is known as a statically induced EMF, while this principle of dynamically induced EMF used in the working of DC generator and alternator. So these are the 3 points which gives the small comparison between statically and dynamically induced EMF. Now one and last important point is Fleming's right hand rule. This rule states that hold out the right hand with the first finger, second finger and thumb at the right angle to each other. As shown in the figure, we have to put our 3 fingers at right angle. So first finger and second finger and thumb we put at that in a right angle. Now for a finger, that means first finger is always represent the direction of line of force. Force is known as a magnetic force, and the thumb points in the direction of motion or applied force. So our thumb is indicating the motion and second finger gives the direction of induced current. So third finger in the direction of current. Also see the second figure and we understand what is the Fleming's right hand rule. As shown in the figure, there is there is a magnetic field from N to S. So first finger put in the direction of magnetic field. Now our conductor is getting force upward direction, so put your thumb into the upward direction. Now when we put your right hand in this situation, you get your second finger comes outwards to the screen or a plane, then current in this direction. If similarly force is a downward, then you put your thumb into the downward, then current will go inside the paper. So current direction is inside the paper. So always we put our right hand first right hand as a three finger at right angle, and we check the direction of current flowing through it. So it is very useful to find out the in which direction current will be flow or in which direction current will be get force. Now using one video we can understand what is Fleming's right hand rule. Similarly there is one Fleming's left hand rule. By video we can understand both the rule.
Fleming's rules help us to predict the movement of a current-carrying conductor placed in a magnetic field and the direction of the induced current. Fleming's left-hand rule. When a wire carrying electric current is placed in a magnetic field, the magnetic field induced by the wire reacts with the applied magnetic field, and the wire experiences a motion. Fleming's left-hand rule helps us to predict the movement. Fleming's left-hand rule. Extend the thumb, forefinger and the middle finger of the left hand in such a way that all the three are mutually perpendicular to each other. If the forefinger points in the direction of the magnetic field, the middle finger in the direction of the current, then the thumb points in the direction of the force exerted on the conductor. Fleming's right-hand rule. A current is induced in a coil of wire whenever there is a change in magnetic field. Fleming's right-hand rule helps us to predict the direction of the induced current. Fleming's right-hand rule. Stretch the forefinger, the middle finger, and the thumb of the right hand such that they are mutually perpendicular to each other. If the forefinger indicates the direction of the magnetic field, the thumb indicates the direction of motion of the conductor, then the middle finger indicates the direction of induced current in the conductor.
Okay,